All right. Well, welcome everyone to this exciting technology advice webinar on schema design best practices for federated GraphQL APIs, sponsored by Apollo. As we continue to see the increasing adoption of GraphQL in modern applications, one of the most crucial aspects that come to the forefront is designing robust and extensible schemas. Today, I'm excited to hear from two experts in the field as we navigate best practices, challenges, and strategies in GraphQL schema design. I am pleased to introduce Joe Devine, Solutions Architect EMEA, and Tushar Bhushan, Senior Solutions Architect at Apollo GraphQL. Thanks, guys, for joining us today to share your expertise. I'm excited to see what you all have to share with us, so why don't you go ahead and take it from here?
Cool. Thanks, Jesse. Appreciate the intro. Yeah, welcome to this session on schema design best practices with Apollo Federation. Let's get right into it. So we'll kind of cover a quick agenda to begin with. First thing we really want to understand is a quick overview of Federation, what entities are, why you should really think about thinking in entities. Then we'll kind of cover into some more best practices around how do you want to design your schemas so they're more demand oriented and expressive. We'll also cover nullability concerns, how to use abstract types, deprecations, and some of the tooling that you can leverage to make that easier. And then finally, some cross-cutting concerns as well. So before really diving into entities themselves, it's kind of good to have a quick refresher on what entities are and how does federation really work. So let's refresh ourselves on some key concepts here. We'll take this really simple example. We have a set of subgraphs, the products, reviews, and user subgraph. Each one of these subgraphs are connected to their own data stores, which is where the data is actually coming from. The Apollo router then exists on top of all your subgraphs and acts as kind of a unified layer, which will compose your schema across all of your multiple subgraphs, and then use Query Planner to intelligently figure out, based on the query that's coming from your clients, how these requests need to be routed to the appropriate subgraphs. So for example, in this case, you might have a mobile app or a web app, and then both of these are connected to your Apollo router and can query the GraphQL schema as if it were just a single unified schema. Really what's important to understand here is the entities as objects and interfaces are all defined within your subgraphs. The router itself is only responsible for composing your subgraph schemas, but doesn't really create any schemas in and of itself. So what is an entity? So the really simplest way to think about entities is it's basically a GraphQL type that has this additional @key directive. So the @key directive just takes in a single argument, fields, and the fields themselves define a unique identifier for that particular entity. So you kind of think about it in terms of a primary key, for example, for your entity. You can also then use these entities and reference them across other subgraphs. So in the previous example, we saw that the product subgraph defines a entity with a UPC, name, and description, with the key field being UPC. Let's say we wanted to extend the subgraph or this entity in another subgraph called the review subgraph. And the review wants to be able to reference the product that's actually being reviewed. So in this case, we can just use a stub of the original product subgraph, in this case, the @key field, and only define the key fields in our stub. And this way, the review subgraph can reference this products type as if it were a kind of a native entity of the product subgraph itself. You can also extend entities. So we're not just limited to referencing them, you can now start including, for example, if we wanted for a given review, product, return a list of reviews corresponding to that product, we could do that by just including this reviews field at the bottom of our products subgraph stub, and now automatically every time you query for a given product, you'll be able to access the reviews field for that product as well. So that brings us really well into entities and why you really want to be thinking in terms of entities. So let's say that you're embarking on a new federation project or adding new subgraphs to an existing type. It's really important to identify which types in your API look like they play the role of an entity. So what does that mean? The types that you choose to be entities can also help you make decisions about where subgraph boundaries should be drawn. And so it allows you to create them based on concerns. So by splitting up your graph this way and extending entities, you're introducing a level of complexity that many teams and organizations aren't used to. So how do you prevent or how do you ensure that decoupled teams don't generate a tsunami of breaking changes as and when they're updating their graphs? Really, the answer is to use a schema registry such as Apollo Studio or GraphOS, and it's really something that we recommend all federated graphs use. This ensures that no one person can make a change that breaks composition for everyone else, and really puts you guardrails in place around evolving your graph via a transparent process. And that leads us really well into our next best practice.
Yeah, thanks, Tisha. So yes, that leads us into designing schemas in a demand-oriented way. Now, this is one of the key things we recommend when it comes to schema design best practice. Now, one of the real powerful aspects of GraphQL genuinely is that it provides an abstraction between client and server. And what that does is that allows you to have the separation of concerns and build out a schema that really services the clients. You can really think about what is the data that the client needs, what is the format they need, and be able to abstract that implementation away. So just say here, prioritize client needs. And yeah, not just one client need. Your schema should be built with all of your use cases in mind. And as part of that, we try and build in the language in our query names and our mutations that really cater for what these use cases are. Now, one situation we see where is the opposite of that is when we start to include some of this implementation detail. And what we mean is mutation names and things that could be like posts and puts and that kind of stuff that's very much REST language tends to be a case of where we see that the logic is essentially being brought through to the client. Whereas one of the biggest values of GraphQL is you can say, I just want this data in this format. Don't need to know where it comes from. I don't need to know what subgraphs resolve these data. I don't need to understand the business logic, and I don't need to have that clogging up the client and affecting performance. So an example of that we've got here. So some REST focused verbs, for example, we've got post product and patch product, which probably look really familiar from general REST APIs. But what we'd recommend here is some verbs around create product, update product name, update product description. And what these do is these make the schema very easily readable, very easily understood. And in essence, kind of self-documenting as well. It's quite clear here. There's no ambiguity for the consumers of the graph. And especially as you scale a super graph out and you've got more and more consumers of a single schema across multiple data sources, you want to make sure that your schema is very easily understood and essentially self-service. So by having names like this that are easy to interpret is incredibly powerful. There's one thing to notice here as well. We've broken, you can see in this example that patch products have been broken up into update product name and update product description. And what we're doing there is removing the ambiguity between, do you patch product with name or description? There's some nullable fields there. Or whereas in the client focused verbs here that we've got, there's that ambiguity has been removed. You know exactly how these are used and much more atomic. But Tusha, I know you're going to go into this a little bit more in some more detail in the next one. So
yeah, thanks for setting me up perfectly for the next one. And just expanding on this idea of expressiveness, you really want your GraphQL schemas to not only convey meaning about the underlying nodes, but also describing the relationships between them. And we'll kind of talk about this in a little bit more detail. So there's a lot of different dimensions to schema expressiveness. And in this case, or specifically for this talk, we really want to focus on some tactical concerns. So first thing kind of goes without saying, be consistent with how you name things. Generally, given that you're composing across multiple schemas and multiple subgraphs, it's really important to make sure that there's some standard naming conventions to prevent ambiguity. So for example, you also want to design your field around specific use cases. So different approaches to naming field names for different subgraphs won't provide a very consistent or intuitive experience for clients. So really the start of a migration to a federated graph is a good time to take stock of what naming conventions you're usually using, which conventions should be standardized, and which team or which convention should be deprecated or have field rollovers. So as we've discussed, a GraphQL schema should be designed around product requirements, and ideally any fields that are added to it support these requirements. What this means is having more finer grained mutations and queries and having guidelines in place for API contributors to better understand how to design and add to their subgraphs. So for example, taking a really basic example with a query which has multiple subqueries. In the first query you see we're fetching users and the first name for a user, whereas the second one we're fetching products and a description. So it's not really clear, given the inconsistent naming, whether the first query is a get or whether and like how to use it, versus the second query, which is marked as get products, but then is inconsistent with the first one, and so generally causes a lot of confusion for your clients. Another thing really to consider in terms of fine-grained mutations, extending on kind of what Joe was talking about earlier, let's take a really simple example. Again, here we have a query type. The query is called user. It accepts 2 arguments, an ID and a username, and just returns a given user. So right now, it's really unclear looking at this, what happens if we pass in just ID or just username, or what happens if we pass in both or neither. It's really unclear, given the way that this is set up, how a client is meant to use it. How about a better approach would be something like breaking this out into multiple queries. So in the first case, we have a user by ID. We can leverage nullability in this case by indicating that the ID always has to be available. And therefore, from your data loader and your subgraph perspective, you can always be ensured that there's some safety when these queries are being called. And then similarly, we can break apart the user into a user by username, and again, accept just a single argument username, which is non-null. So it just generally creates a more predictable experience for your clients. This approach really applies to mutations as well. Again, kind of extending on the example from the previous slide, you can see here that we have multiple mutations, and each one of these mutations only accepts a single input argument and is only responsible for making a change to that argument. So in this case, adding a secondary email only takes in an email address and will only modify the secondary email for a given user. So one caveat, however, to note is that if certain values need to be updated simultaneously or not at all, that's kind of the one scenario where you would want to have a more coarse-grained mutation. But generally speaking, for the majority of use cases where that's not the case, a finer-grained mutation is definitely prevents ambiguity and concerns for your clients in the future. The last real tactical concern is documentation. Documentation, can go a really long way in terms of empowering your developers to how to use your graph. And the GraphQL spec itself defines documentation as a first-class feature of all GraphQL type systems. In fact, it goes so far as to say that all types, fields, arguments, any definition, including directives, should all have a description unless they are self-descriptive. So for example, we'll take an example here on the right. You can see we've got a query type with a single query products. It accepts 2 parameters, first and after. 3 parameters, first, after, and product type. And then it returns a product connection. In this case, we also want to make sure that our documentation standards are also standardized. So that means all of our field descriptions have some consistency between them, and it's really easy to understand just parsing through this, what these fields are, how they work, and what accepted values are. This will just generally ultimately ensure consistency for client developers.
Thanks, Tisha. Yeah, so the next best practice is around nullability. Now, nullability can be a really important one to consider, and really the main reason for this is around backwards compatibility. So there can be real issues that can crop up depending on how nullability is implemented to begin with, and if there's any changes moving forward. So consider, for example, there's a query that returns a field that is not null. You could have built a client app that is confident that there's always going to be data returned. If that then becomes nullable, you might end up with a null response coming back to the client, and the logic would not be there necessarily to handle that state, meaning it would be a breaking change. And the same as well, vice versa on an input type. If there was previously a nullable field, so maybe you were getting a user object and maybe it took name and email address, and maybe some of those fields were nullable. If at some point that becomes non-null, the client might not have the user flow to provide that information. Again, would be a breaking change. So it's really important to think long-term about how nullability is in place. And this example here as well, sorry, Tisha, just go back to the previous.
Yes.
One, yeah. So here's just following on from the example in the documentation. So this product, it takes this product type. Now, it's not crystal clear here that, because we've got a nullable type. So it could either, you can provide a filter to products. So when you get back a list of products, you can provide a filter for whatever that type is, or it says that you don't have to pass anything at all, which might mean that it's assuming you're going to return everything. But really what we'd encourage in terms of how to properly implement this is to try and avoid a situation where you have these nullable arguments on input fields. Rather, what you can do instead, if it does need to be, and you really want the state where I just want to get all the products and I don't want to apply any, you can apply a default value as well. So in this example here, we've got product type is all if nothing's applied. And we've got a mention here as well just about non-null entity references. Now that's really important when you start thinking about, especially as you scale, if you're referencing fields on an entity that maybe you don't have control over and you can't guarantee that data is actually going to get returned, forcing that as non-null on your schema could possibly be an issue if the data is unavailable. So it's really important to think about where that data is being resolved from, and how that's going to work, and try and avoid those situations. So definitely one to consider as well, especially as you scale. And quite often you find that as subgraph teams grow, possibly even internal organizational boundaries could occur. So not having control over that data could become even more consequential as well. So really important one to think about in terms of backwards compatibility.
Cool. Switching gears a little bit and talking about abstract types. We also have some general best practices that apply really well to abstract types. Before diving into how the best practices themselves, quick refresher, GraphQL defines two abstract types in its type system, unions and interfaces. So abstract types are really powerful tools in expressing relationships between types in a schema, but really when adding interfaces and unions, it's really important to do so with a clear understanding of longer-term implications for how to manage these types. So for example, a common misuse is to simply use them to express a contract for shared fields between types. A better really approach is to reserve them for when you need to return a set of objects from a field that can represent a variety of different types with some fields in common. Really, the number one tip here is if your interface isn't being used as an output type, then there's probably a good chance that you don't need it. So let's talk about that in a little bit more concrete terms, right? Let's take in this case, this example on the right, we have this pet interface that just defines a breed, and we have multiple implementations of this interface, cat and dog, each that define specific fields to their particular type. And we have a single query called family pets, and this returns a list of pets. So in terms of the way a client would actually interact with this, is that when they're making a request for the family type, they can retrieve the shared fields as usual, and then use fragment spreads essentially to be able to query for the cat and dog specific fields. So if there's really not a use case for querying both cats and dogs simultaneously to return from a single operation, then the pet interface really doesn't serve any notable purpose. Instead, it would really add more overhead in terms of evolvability for your schema, because you would then be responsible for ensuring that all of your interfaces conform, or all of your implementations conform to your interface. So consider if you wanted to add a new field to your interface, you would also need to ensure that your all of the types that implement this are also updated accordingly. So this is really important for non-federated APIs in particular, really because you might have concerns that spread across subgraph boundaries, or you may need to coordinate across multiple teams. And so in that case, it could just increase the amount of complexity and overhead. Another thing to really consider is trying to avoid really semantically pointless interfaces. So in this case, again, relying on that previous example, you can see that the fragment spread on cat and dog will retrieve the individual fields for those. But if there isn't a use case where you need to represent both of these fields in your client side, it's not really providing any value. So really building on this, you should really only add interfaces with careful consideration, because subtle breaking changes can occur. And let's consider that with an example. Now, in this case, we're taking our existing pet interface, but we're implementing a new goldfish type. So now on the return type for the family pets query can now have cat, dog, and goldfish. But the original previous query here for get family pets only has fragment spreads for cat and dog. So we could subtly introduce a breaking change for our clients if they're have not updated their queries to account for this new interface type. So in order to actually make this resolvable, we would have to then add an additional fragment spread for goldfish and then include any of the fields that are specific to them. So this can just kind of introduce subtle breaking changes to your clients. Finally, the last consideration when using abstract types is they can be tricky when to resolve when they're reused across different subgraphs. And we'll kind of cover some cross-cutting concerns like that later on. But yes, it's also something that you want to keep in mind.
Thanks, Tisha. That leads us really nicely into this one. So what happens if you did implement it in a way that you want to change? What mechanisms do you have to revert that change or update? And that, deprecations is an important one, because especially when you've got numerous subgraphs, you've got lots of people consuming your supergraph schema. In deprecating fields can be a really tricky thing to navigate. So that's why we recommend the deprecated directive. And what's really nice about this is simply by applying this to wherever the field lives. So you can see here in this query, we've got this top product is going to be deprecated, and we give it a reason as well. So it's a directive that takes a reason. And what this does is this provides information to consumers to say, look, this field, although you can still currently use it at the moment, is being deprecated. This is where we're moving to. And what's nice over that time frame is if you leverage Apollo Studio, you can use the telemetry and the feedback of the operations and how they're being used. Is that you can, in your operational checks, you can see how queries are dropping off. Are they still being used by which clients? And then make sure that you're not pushing out any kind of breaking changes. So there's a screenshot here of exactly that, those operational checks. So it's saying here, look, this thing that you're deprecating now and that you're removing is still being used by these clients. You can see how long ago, you can control the time frame, and that just gives you really good control over not just removing fields away and breaking what the clients are currently using or what they're querying. Really important when it comes to things like mobile apps and stuff that might be stuck on certain versions with specific queries, and you need to incrementally roll that out. Really gives you control over that as updates come through from the underlying subgraphs. So it can be, a really powerful tool for that.
Cool. And let's say you do run into an error state. What is kind of best practices when things don't work the way you expect them to? So this is kind of leads really well into our next best practice and how to really handle errors or think about errors as data. So GraphQL kind of has a unique feature in that it allows you to send both your data response and your error response in the same response, or rather data key and error key in the same response. So the error key forms a part of the GraphQL spec, which details various error-related behaviors. But really, this isn't our other option. As I mentioned earlier, you can kind of adopt an errors as data approach as well. And this way, you're codifying the various error states in your schema itself. So let's consider that with an example. In this case, on the right, we're seeing a example GraphQL response. Our data user is null, and the reason why is within this errors key. As you can see, it says it's not found. There's also a message that describes that with the given login, this user wasn't able to resolve. That's awesome. But consider this from a client perspective. If a client wanted to then handle this error in a client-friendly way, it would be up to the client developer to be able to extract the relevant information, and then it would also need to figure out how to display that information to its users. So instead, let's take a slightly different approach where we're representing our errors as data when communicating other possible states. So really, we're co-locating both the unhappy and happy paths together such that client developers will find it much easier to consume your graph and reason with different error states. So let's take a look at an example of what this might look like. So first off, we're adding a new account subgraph with a user entity and a simple me query that returns the user in the account subgraph. Then in the product subgraph, we're extending that entity and user entity with a suggested products field that returns a list of product results. And you'll notice here that the product result itself is a union of both the product and product remove error types. So rather than really throwing the error in the errors key, we've actually acknowledged that a product can be removed, could be removed, and that's an expected state for your client developers. So this way, we're kind of encoding both the happy, which is the product state, and the unhappy, which is the product remove error states. So you could also then query this data for suggested products for the currently logged in user, or use inline fragments to kind of handle the different return types of the union. So through this example, we can see how errors as data help support graph consumers in a few compelling ways. First, creating a union of happy and unhappy paths provides kind of type safety for these different states, and then also leads to more of evolvability for your schema as and when these states change. Finally, it also lets you tailor your error data to client use cases. So in this example, you can see that on the product remove error, we have a query for similar products and name and SKU. So this way, when a client developer is trying to develop the UI for this particular use case, they can then use the inline fragments to display both a happy path where the product is available, but then in the scenario where it's unhappy and there isn't availability, it can display similar products as well. It's also important to be consistent across your graph in terms of how you handle errors, including details on when to include your errors in schema versus in situations where you may not want to include in your schema.
So that brings us to managing cross-cutting concerns. So cross-cutting concerns becomes really important as your supergraph grows. So really what we're talking about here is the situation where there are fields and identical types really across different subgraphs that can be resolved in those different subgraphs. And we refer to those as value types that different subgraphs are equally able to resolve. Now we can handle that really nicely with federation. So we can apply a directive that we call shareable. And what that does is that gives Router the information when it's building out its query plan that say there's type A has fields A and B in subgraphs A and subgraph B. For example, we've got subgraph A and B here. What we're saying here is that if we're doing a query that is pulling almost entirely types from subgraph A, it can also resolve position from subgraph A. Or if our query includes types from purely subgraph B, including position, we don't need to make an additional call to subgraph A to resolve that data. Subgraph B also has access to that. Now we've got an example here of the reload page info object. So that could be defined. So if you're following that pagination spec, it might be that you've defined this type in multiple subgraphs. We see quite a lot. That's an example where you say this can be resolved because this will come back in whatever the data source is that we're using in the given subgraph. But it could be anything. It could be that subgraphs A and B have access to user information. And it could be that you can get ID and name from the two different data sources, or even the same one from each subgraph A or B. So by being able to apply shareable to both either the types that we've got here, or can be applied to fields as well, allow to make those optimizations for better query planning. But with that comes complication in terms of what happens is we make incremental change and we're introducing these fields. So we also have inaccessible. And what happens here is that imagine a case where we've got subgraph A and B without that inaccessible directive. Now, when it comes to composition, what we'd find in the supergraph schema is type position with X, Y, and Z, with shareable at the type level in both A and B. That would give root to the idea that it can resolve position with all of its types from A or B, but actually B doesn't have access to Z in its underlying resolvers. So the way that we can solve for that is by marking it as inaccessible. We're then able to remove that from the composed supergraph, making sure that when the query plan is in place, it can comfortably resolve the correct data from both subgraphs. So it's a really powerful tool, and the combination of both shareable and inaccessible allow us to manage this over time, make incremental change. But the one caveat is there is some possible complication with this. If you've got multiple subgraphs that are resolving similar data, it's very important that you're careful about, do you have duplicate resolver logic across these subgraphs? Are they all talking to the same data sources? Possibly. Is there conflicting data coming back? All those things that need to be considered. So you do have this ability, and it is a really powerful tool, and actually can provide optimization if used correctly. But there is some complexity that comes with it. So there's risk with it as well to be considered. So definitely something to think about, but can be a really powerful tool.
Well, thanks, Joe. So those are really all of our best practices. We, as just kind of wrapping this up, wanted to share some quick summary of some of the things that we've discussed today. So first thing really is any general GraphQL schema design best practices apply to your federated data graphs too. These aren't different. But the one thing you want to consider is that these are now being handled across a much larger and distributed scale. So how do you make that easier? Well, the first real approach here is governance. Governance standards really help you enforce these standards. It helps you prevent kind of entropy from leaking into your schema and then causing divergence and other schema issues. And generally will help you evolve it in a way that's always usable and predictable for your clients. Communication is really important. As you've heard, there's always cross-cutting concerns. There's issues with nullability. There may be concerns with unintended breaking changes. All of these things may happen or will happen. And therefore, it's really important to make sure that you have automated ways to make sure that your schema registry is sending Slack notifications, for example. GraphOS also provides a lot of this functionality. You really to make sure that your subgraph teams are updated whenever specific changes are made to your supergraph. And then finally, as your subgraph owners propose schema changes, your schema will obviously evolve. It's really important to then leverage on things like observability and tooling to make sure that as your schema evolves, you're not inadvertently causing issues for your clients. And again, GraphOS provides a lot of these features inbuilt, which will really help kind of make your graph a lot easier to maintain and evolve in production environments. With that, I did want to mention that I know that this talk was way more high level. We do have a much more hands-on workshop that's happening on September 28th. So definitely encourage folks who found this content useful to check that out. That's going to be a lot more hands-on and give you a lot more context. With that, I'll take a pause. Any questions from folks on the call? Happy to address anything that wasn't clear. Yeah, open questions.
Fantastic. Well, thanks, guys. That was awesome. And we do have some questions. So I'll start with the first one. Y'all ready?
Mm-hmm.
All right. So this person's looking for you to describe a good use case on when to use nullability.
Interesting. Joe, do you want to take that one?
Yeah, so I think we touched on it a little bit in that section about when you're referencing entities. I think when you don't have control over whether or not data is going to get returned is a good situation where making a field nullable is going to prevent situations where that data doesn't get returned. And I think the opposite of that is true as well when it comes to things like input types. It's really important or can be really powerful to make sure that having a non-null input type removes any kind of ambiguity about what fields need to be provided on on those, rather than, because as Tushar mentioned earlier, it removes that ambiguity between, do I need these fields? Do I need to apply these on this input? Having a non-null field on that input type is going to make it crystal clear how to apply that.
Awesome. Well, hopefully that helps. A lot of things to look out for with breaking changes we talked about before around nullability. So y'all pay attention to that one. Now, how do you define, because we're talking about subgraph maintainers too here. So how do you define subgraph boundaries?
Yeah, I can take that one. That's definitely more of an art than a science, I would say. Just generally speaking, you want to define your subgraph boundaries in terms of use cases and the domains that they belong to. So what we see most customers do is have a domain-specific subgraph. Also, another general best practice to be aware of is it's generally easier to split larger subgraphs into smaller ones than it is to do vice versa. So really a good recommendation, especially if you're starting off on your journey, is to start with a minimal number of subgraphs. And then as your requirements change or you need to start breaking apart things for ownership or defining more kind of strict boundaries, that's when you would want to start considering, how do I want to split apart these subgraphs? And one last thing really to consider in terms of the number of subgraphs or how many subgraphs is consider some of the costs that might be applied to network calls, for example. So if the router would potentially need to make a call across multiple subgraphs that are distributed, that may introduce more network latency versus if it's all kind of co-located within a single subgraph.
Okay, awesome. Now I want to talk a little bit here for this person about enum values, right? So what's the best practice for adding and removing those?
I could jump in on that. I've had lots of enum conversations this week. It's a nuanced one, actually, enums, because they do, the interesting thing with enums is they do actually behave quite differently based on how they're actually used in the schema. So it's yeah, it is quite an interesting one. So again, if you're trying to remove fields and things, obviously you've got things like inaccessible and stuff like that. But I think with enums, it's quite important to know how they compose as well. Because, for example, an enum could be used as a field value, for example. If that's the case across different subgraphs, it's worth being aware that that's going to compose as a union. So you're going to have, say, you've got enum in subgraph A of value ABC, and then in subgraph B you've got C, BCD. The result is going to be ABCD. So you're going to have that union result that could be either the values right across those subgraphs. Now, I think because it's tripped a few people up before that I've spoken to this week, is that actually if you get as an argument, the way that these things get composed, it's actually the intersection. So in that case situation, we had ABC and BCD, you'd actually only have BC. For good reason. It means that it guarantees that you can't provide an incorrect value. So this is really important to think about when you are adding and removing fields. How, because when you add it to your subgraph, it's important to know how they're going to end up in the supergraph when it actually gets composed. And there's another situation as well where maybe you do both of those things. And if you do both of those things, then composition is going to require an exact match. So that, as Tushar mentioned, the communication is going to be key there in actually managing that. And in one of the situations I was talking about this week is actually you can use it as your key. So when you're talking about entities, you can provide an enum. In that case, it will actually do a union, unless again it's being used as an argument somewhere else as well. So it's really critical how it's being used across the graph. So yeah, it's funny you say it's one to think about, especially with enums. It's a communication. I think it's quite a common hurdle. I think with distributed setups of subgraphs is how do you manage these values? How do you govern these? And I think Federation does a really good job of understanding how it's being applied and giving you the appropriate composition. But you can get caught out if you weren't expecting it to compose in that way, and you'd be like, "Where are these values gone?" It's good to know that that's why.
Awesome. All right, so two more. One, can
Perfect.
the fields mentioned in entity keys, we're just talking about entities, right? So can they be optional?
Yeah, that's a good question. One thing to understand with entities, and I guess an analogy that might be helpful, is really to think about your keys as a primary key, or as you would consider a primary key in your database, right? So that kind of forms the least common denominator identifier, or the minimum detail that you need to provide in order to be able to extract a given record in the traditional database case. So really porting over that kind of understanding to entities, very similar approach. Anything that you define in your key fields is really meant to act as a primary key for that entity. So what that means is
Mhm.
the query planner expects that if I give you a set of key fields, I expect to get a response for each of those key fields. Obviously, nullability and things come into play. So some, fields within your type may be null, etc. But really, the understanding is if you're setting something as a prime or as a at key for your entity, then the router will expect to be able to retrieve an individual record for that entity via its key. So long-winded way of saying, no, it's not optional.
Got it. Required.
Exactly.
All right, last question as we wrap this. Well, I'll have another question after we get through the chat questions. How do I support a search use case in a federated data graph? That's a good one.
Yeah. So that ties in quite nicely, actually, with what we're just saying about how entities work with keys, because I've had some conversations recently where, so I'm assuming this is what's meant, is that you can have a situation across a distributed supergraph where subgraphs maybe have access to elements of an entity's data, but maybe different amounts of it. So, for example, product. You could have, a data store that's got all of your product information, all of the products you've ever had, and then maybe another one that's got the products that are available in a given store today. I don't know. This is just a subset. It's going to have a different amount of information. Now that can actually cause some challenges, because when you're resolving this data, if you think about what the type's actually going to look like, it's going to look very similar, and how you build your supergraph to resolve all the data you require in a certain situation, and how do you make a single query. And again, you want to make sure that, because we're building out the supergraph with the schema even to really service the use cases, how do I have I want one search query that gives me this data and this information across everything. Now, you could have lots of different queries and business logic and things to put this back together, but one pattern that really works is potentially another subgraph for that use case that actually does the aggregation of that for you and abstracts you away from having to do this mapping, and you've got all that business logic in the client, and possible performance impacts again, state management, and all that stuff that we don't need. But that would be
Awesome.
Yeah, just to add to
Okay.
that as well, one thing to consider, as we'd mentioned earlier, or I think there was a question earlier around subgraph boundaries and how you want to define those. Well, search is really another domain, right? And so a good way to think about that is, like I said, like Judd mentioned, given that search is its own domain, that's a really good use case for why when you might want to have a separate subgraph versus, using an existing one. So, yeah.
Awesome. All right. So this was one of those deep webinars. So if I'm like you out there watching, I want to know from these guys, where do I go next? Right? Where are some places I can go for information? Help me out.
Absolutely. So I'm going to plug Apollo GraphQL. Our documentation page is really, it's vast. There's tons of information there. Really, if you are interested in learning more about federation, GraphOS, things like observability, some of the things that we talked about tooling-wise that can really help maintain and evolve your graph. I would highly recommend checking out our docs at apollographql.com. And then besides that, I think I mentioned this slightly earlier, but we also do have a hands-on workshop as well. So another really good way of bootstrapping your way to getting your federated graph up and running is really to check out the workshop. I believe that's on September 28th. But yeah, that's another really good option as well.
And just to add as well,
Awesome.
we've got a big bunch of Odyssey courses as well, which really recommend. And
Good call.
a nice feature of those is that you can get your LinkedIn badges as well. So you're gonna once you complete
those are cool. That's cool. Good share. All right, guys, thanks so much. That was awesome. And thank you, all of you out there, for joining us for our discussion today. I'd also like to extend a special thank you to our sponsor, Apollo. Joe, Tushar, y'all did great. Thanks for sharing your expertise with us today. Now, whether you're a subgraph maintainer, client developer, or anything in between, we hope you picked up some actionable things to take back to enhance your own schema design. We just talked about this Apollo schema design workshop. That's on September 28th from 9 a.m. to 12 Pacific time. If you look over in your chat, there's a link where you can sign up. I hope that I get to see you there so that we can all get better at designing these schemas. Hope you all have a great afternoon. Bye for now.
Thanks, everyone.